Yeah, thanks, Stephen. And also very happy to be at this conference again. And thank you to the organizers especially, because I know how hard it is to organize this, having done it a couple of times. I really appreciate that. And I'm going to tell you about some work done while I was at UCID. And I need to say that because I'm going to, before I say any complimentary stuff about Quantinuum's devices, I'm doing this with my UCID hat on, not with my IBM hat on. We're obviously better than them, and you should not use their devices. You should use IBM services. Anyway, so now UCID hat. I'm going to tell you about this fun work I did with some people at Boulder. And someone at Quantinuum, Michael. The main leaders on this project were some postdocs at Boulder, Ollie Hart and David Stephen, and advised by Rahul Nankishore. And the way this project started, I always like to tell these fun stories. We had this idea that we wanted to play a game on a quantum computer. And so we went to, my friends in Boulder went to the local Quantinuum office and asked this guy, well, we want to play a game, so can we? Luckily, he was happy to play with us, and we didn't have to sort of lock him in a warehouse and make him go through some kind of sequence of quantum game torture devices. And yeah, I should say as a disclaimer, no one at Quantinuum was harmed during this project. So here's the point, in case you fall asleep because you didn't get enough coffee in the break. We look at some kind of quantum non-local game, which is usually played with GHD states. We'll get there if that doesn't make sense to you. And we basically replaced these GHD states with topological states, the idea being that this would buy you some protection. And I'll explain why you might expect that. And what we found when we implemented this was that, indeed, using topological states, you do perform much better once you have a bit of errors, which are sort of unavoidable whenever you start implementing things. And here's a little picture of the circuit we did. I'll explain all this later. So yeah, if you want to take anything away from it, basically using topological states to play this game is a bonus. Cool. So a bit of motivation. I was making this talk on a train from Kyoto to Tokyo like 2 days ago. I don't know if you can tell. So that's where this inspiration came from. But I was thinking about why do we do this? Which always you kind of have to retrofit. When you do a project that's kind of fun, then you're like, well, why did I really do that? Why was it like in the back of my mind that I should think about this? And I think the real thing that's interesting at the moment with this sort of topological codes is using them to implement some kind of full-scale, fault-tolerant quantum computation. We're kind of pretty far away from this point, but people have been doing some really interesting things lately. So one thing, or a few experiments that have come out, like from Harvard, Quantinuum, and Google, here are some little slides I took from their papers, is that you can prepare these topological states, really physically prepare them, not just put them in your classical computer and stored as a state vector. And so that's a very interesting development. We can prepare these states and maybe do some measurements on them. But it's still very far away from actually using them to do anything useful. It's kind of like you prepare it, then you're like, oh yeah, what do I do now? I caught, like the dog chasing the car. You caught the car, you have these really amazing quantum devices that can make these states. And then you have to start thinking well, what do I do once I make them? And so there's the next step up the hill is trying to think of some kind of funny task you can use these states to do that will give you some advantage, there's some reason you actually made it. And here's just two works I kind of like on this, vaguely in this direction. One is from Arkin in collaboration with people, I think at Davis and also Quantinuum, where they looked at using some adaptive circuits to prepare topological states faster than unitary circuits. And then the other one is from Google, where they tried to use topological states to suppress errors and show that they kind of were maybe near the cusp of doing that. And here's our work, which fits in this category, where we sort of tried to come up with some task that this game you can only play quantumly, where having topological states will buy you something. So there's actually a reason to use them. And I think there's probably a bunch more, more interesting things even that you could think of to do down here before we're really in this quantum, utility regime. So that's a challenge, I guess, to think about. Good. So the outline for the talk is I'm going to kind of go in order of things I know about. I'm going to start by telling you about topological order and topological codes, and then move on to things I'm increasingly unsure about. So contextuality, sort of, a bit daunting that Stephen's sitting in the front there. Hopefully I don't say anything wrong. You can correct me. And then I'll move on to a little bit about the experimental implementation. And that'll probably get completely wrong anyway. So let's go. What is a topological code, which has sort of formed the basis of this topological idea of topological order? It's something where you have a lattice. So maybe you're inspired by some experiment with superconducting qubits on a chip, and they have some nearest neighbor connectivity, and you want to fit your checks onto this connectivity. You also have the idea that essentially the errors should follow the locality of your physical interactions. So you have these local checks, and you need to deal with at least all local errors that are going to occur. And luckily, there is a family of codes that does this. They're called topological codes, and they have a really nice connection to physics. You can view these code spaces as the ground spaces of some Hamiltonian that has only local interactions. And this gives you some window into connecting this, this sort of type of codes to ideas we have from condensed matter physics going back to the 70s, say. And this brings in a natural notion of equivalence. So these codes are not like really rigid things. They have some deformability. And the idea is if you sort of deform things a bit, all of the properties, there's some universal properties like the fact they can correct against local errors that should be robust. And this idea is kind of important for this project because it's like the idea that underlies why we should use these states rather than this other class of states to play these games. And there's two kind of versions of this equivalence relation. One is like local unitaries, so you might want to just take some gates and do a local unitary in your code, and that should essentially preserve the class of local errors that you're robust against. The other version is taking this Hamiltonian picture and sort of deforming the terms in the Hamiltonian, which is sort of approximately described by a local unitary, but there's a bit of subtlety there. Okay, so a little bit more detail about how to define a topological quantum code. So here's like a toy picture I drew in 1D, although these things generally live in 2 dimensions or higher. And these code spaces, which you can think of as the ground space of some Hamiltonian, are defined by essentially a product of like local checks. So you have these projectors locally onto satisfying the check. These all build up into some big projector onto your code space. And your Hamiltonian, which sort of stabilizes this code space, let's assume everything's sort of commuting for simplicity, is just like the minus sum over all of these checks. So when you satisfy them all, you're going to be in the lowest energy eigenstate of this Hamiltonian. Okay, what is the sort of error correcting property of this code space? If you take any local error, which is sort of coupling to some environment, that's going to take a local form due to the physics of the system, and you sandwich this thing into your ground space, it can't learn anything about the ground space. So whatever information, quantum information is encoded there, this error can extract nothing from because it only sees, it acts like the identity within this space up to some constant. And this constant can be 0. So this error might just take you out of the code space. But essentially, if it maps you from the code space back to the code space, it can't do anything bad. OK, cool. And this is essentially the error detecting condition of nil-Laflamme. I had that up a second ago. And OK, there's some nice line of work saying that what does this kind of code property buy you for these Hamiltonians when you think of them from a condensed matter point of view? It buys you that you kind of have stability of this code space. So if you take this Hamiltonian and you deform it a bit, at least up to some constant deformation strength, if you add some extra terms here that are like noise, you will maintain some deformed version of the code space and your error detecting property. Good. And then here is just a little picture of the kind of equivalence we consider. So this is the nice sort of neat version of the equivalence where you just take a local quantum circuit, which is sort of approximately equivalent to the deformation version. And so we actually group these code space projectors into families where we kind of forget about the local details somehow. We wash them out by allowing a local quantum circuit as an equivalence relation. And the motivation for this is that local quantum circuits, or more generally locality-preserving unitaries, will map the set of correctable errors back to itself. OK, and I'm going to do an example, which is the example that we will use in this game, which is the surface code. So yeah, another reason I think this is a really good talk for Kuji is because it features both the surface code and the Ising model, which are like two things, the bread and butter at Kuji. So let me introduce the surface code first. Yeah, my picture for qubits is little blue dots. I'm going to like stick to this kind of color convention for Pauli. So X's are blue, Z's are red, and they have this anti-commutation relation. They form like a Z2 times Z2 group up to phases, and that's pretty much all you need to remember about them. You'll see on this lattice there's kind of boundaries, and there is this dual shading of the plaquettes. And that tells us where to put the different kinds of checks. So on every sort of lighter plaquette, which doesn't quite look white on this screen, you put a Z-type check. On every darker plaquette, you put an X-type check. And then at the boundary, you have these truncated checks where a plaquette's been cut in half. You can check everything kind of commutes because the only time a pair of opposite colored checks hit each other is when they share a pair of vertices. So that'll be like 2 minus 1s. And so this gives you a good set of unfrustrated checks you can measure all at once. What's the phenomenology of this kind of code? Well, if you look at what happens when you have errors, you get these syndromes. These syndromes are point-like. They correspond to a flipped plaquette of one or the other color. Because there's some connection to like Z2 gauge theory, people like to label these syndromes via anionic quasi-particle labels, like E as in electric charge and M as in magnetic charge. And when you have a single error in the bulk, say of X-type, you create a pair of these M syndromes. If you have a single Z-type error, you can create a pair of E syndromes. You can like make chains out of these errors to move these syndromes further apart, so they end up being kind of deconfined points, which means that you can have like a string of errors that only make syndromes at their endpoints. So it doesn't make like a lot of syndromes to move two syndromes very far apart. Okay, so here's just a little picture of kind of hopping over 2 sites, and you can kind of, in your mind, join that up to hop over more sites. Another thing you can do with these that's going to be kind of important in this talk is that you can kind of move these string operators around each other. So what happens if there's like a single M syndrome sitting somewhere? You can take the string of the other kind of error and wrap it around in a closed loop, and you'll find that that's actually just measuring a stabilizer. And what it sees is that this stabilizer has been flipped. And this is often interpreted as some braiding of this string operator with the other string operator, but more about that in a minute. Good. And one more feature of this code, which won't be super duper important, but is important for the example, is that you have a different behavior near the boundaries. So near these boundaries, we've modified things. And what this allows you to do is instead of having this Z2 conservation rule like you have in the bulk, you can break this conservation rule near the boundary. So near these top and bottom boundaries, which are kind of E-type, they have these kind of only these Z-type stabilizers and no X-type, you can create single E particles. So whereas in the bulk, these always come in pairs, near this boundary, you're allowed to pull one out. And you can just check that from the commutation relations of Pauli's. And similarly, near these side boundaries, you can do that with an M syndrome. This has some description in terms of the anion theory known as condensation, which it's not going to be super important in this talk, so I don't want to dwell on it. Okay. And once you understand these boundaries, you see that there's sort of some global non-contractible strings you can apply to this code. One X type that goes across, and one Z type that goes up and down. And they'll anti-commute because they only hit each other at one pair, so they give you a logical pair. They're not going to be the product of any local stabilizers because those always form kind of Z2 trivial loops. And you can see that they nicely anti-commute with each other. Good. So there's some representative illogicals. Yeah, okay. So this connection to condensed matter physics and sort of field theories we use to describe condensed matter states leads to a lot of ideas with these codes. So sometimes you want to take away detail to design things. Sometimes you want to, at some point you have to put more detail back in. But for a few slides, we're going to go in the direction of less detail to get some intuition. Okay, good. And so a nice thing about this family of codes is once you do this local unitary equivalence, you kind of wash out all the local details. Because if you are allowed to apply an arbitrary local unitary circuit, you can just change everything locally. But I said there's some part of these codes that remains invariant under this. And this is exactly what is described by this kind of topological field theory picture. So this just keeps these sort of universal features, which end up being what anions you have, what sort of class of syndromes, and the algebra of their string operators. And it's nice that this is enough to also tell you, given some configuration, what encoded qubits you have. So here, the description is kind of this. There's some block, some bulk block, that could be the surface code or some deformed surface code. There's one type of E boundary at the top and bottom. There's the M boundary on the left and right. And this will already tell you how many qubits you encode, which is a single qubit in this case. And in this like kind of topological world, everything's fully deformable. So any operator you can kind of take, and then you can make an equivalent version that's deformed in a smooth way, and you'll get the same answer. Okay, and so this is where our intuition for designing protocols based on surface code comes from. Good. Okay, and I should say what you can do with anyons. So sort of generally, what's the most general thing you can do with these point-like syndromes? You can fuse them, which just means bringing them very close together and then considering the overall sort of anionic charge or type of the combined object. In space-time, this looks like kind of vertex. The other thing you can do, because you're kind of stuck in 2D at each space slice, is you can braid these around each other. But unlike in 3 dimensions, where you can always kind of find some contraction of a path of one object, one point-like object braiding around another, back to being trivial, here these world lines moving around each other can't be unlinked. They form these kind of braid group because they're stuck in sort of 3 dimensions of space-time. And this gives you a whole bunch of rich phenomenology which allows you to have things beyond bosons and fermions, which we call anyons. It's not quite actually anything, but it's very, very loose compared to bosons or fermions. Good. So this is kind of the full picture. For abelian anyons, you have this like fusion group, which is your abelian group. How do things combine? And then you have this quadratic form, which is basically telling you like what's your exchange statistic. You might ask, okay, and so for the example of surface code, the abelian group is Z2 times Z2. It's just like the parity of E's and parity of M's. And then this self-statistic is just, the only non-trivial one is that you have a fermion for the EM-type particle. So the composite particle of E and M, when you bring them together, that is a fermion. You can kind of check that in the lattice. It's just due to Pauli commutation relations. We're mostly going to use actually full braiding statistics rather than this exchange statistic. So I just wanted to show how you actually get this out of the quadratic form. It's just a neat little trick that if you have a composite particle and you do an exchange on it, you can recouple that to essentially turn it into just a braid of, in this case, the blue around the red. So this information of like braiding a red fully around a blue is already in this self-statistic. And for the surface code, the important one we're going to use is that if you have an E braiding around an M, you pick up a -1, which is also the origin of this -1 exchange statistic here. Okay, cool. So going back to the lattice a bit, there's this really nice picture that people have this intuition for, but in quantum codes, people are a bit more specific. They want to prove things based on some set of assumptions that starts from like qubits on a lattice with local terms. How do you connect these operators you find on the lattice to, and also in deformed examples that are not sort of perfect toric code, more universally, how do you connect these operators you find on the lattice to these abstract things we write in this field theory? There's a really nice paper by Jungwon Ha that basically explains how to do that. And what you consider is you take your kind of lattice model. So imagine there's some sort of lattice model sitting in the background. And we look at these regions. So there's 2 regions here, a P and a Q. They're both just some annulus. So it's like a fattened string. And you think about all the operators you could have in this string that kind of preserve the ground space. And then you take an equivalent. So there's going to be many operators in this sort of annulus that preserve the ground space. And you quotient out by all the local ones. So you could kind of imagine there's going to be maybe some kind of local blobs here that preserve the ground space, and then there's going to be some string-like one that goes all the way around. And you essentially are collecting the string-like ones into some classes up to this local stuff. And this is sort of an essential step, because if you run the lattice, there's going to be a bunch of local details, and you need to have some step to kind of remove these if you want to connect to the more coarse-grained picture. Okay. And so if you have this class of string operators on these regions, you can consider 2 orders of multiplying them. You could apply the Q operator first, then P, or P, then Q. And what Ha introduced was this twisted product. And so what you do essentially is somehow form this kind of link directly with the operators, which is kind of wacky, but it's actually extremely simple. What you do is essentially just take P and Q, and you break space up into the bottom and top half, and then you just decompose the operators with a singular value decomposition into the part that acts on the bottom and on the top. So if there were tensor product operators, there'd be like a string of x's on the bottom, string of x's on the top, and you just break the P up into those two parts. And once you've broken them up, you can then sort of switch the order of multiplication up. You take the product of this P on the bottom first, then this Q on the bottom, and then you take the product of Q on the top, and then P on the top. And you can kind of make this all fully well-defined even when you have operator entanglement. But that's not going to be super important, so I'm not going to write down those formulas. Good. Yeah. And so the thing I wrote on this line was these funny operators. You can multiply Q then P, P then Q, or you can do this funny twisted product where you do like half of P, half of Q, and then undo it. How do you turn these into like these topological invariants that will tell you something about your state? Well, essentially you just take one of your ground states and you sandwich it with this operator, and you see what it gives you. These two turn out to be sort of trivial because it's just hitting your ground state with something that stabilizes it. The operators we're considering are ones that preserve the ground space. But this one doesn't have to be trivial because it's never getting hit by a full operator that preserves the ground space. It's only going to get hit by like half of it at once. And what Ha proposed was basically to use this piece as a lattice version of this kind of braiding invariant in the topological field theory. And he could show that this was like invariant under local unitaries. So if you do local unitaries, the idea is that these rings should be big, and essentially they'll just deform them a bit, and they won't change the classes of operators. And so you can really show that it doesn't change this phase that you get here, this expectation value, sorry, that you get here. Okay, good. So this is the lattice version of these braiding invariants. And now the surface code example. So here, unfortunately, I have slightly different notation for surface code where we're using strings, but I'm sticking to the red and blue. So like red is a Z string, blue is an X string. And if you have this sort of A and B type operators, you can multiply them, A first, then B first, B first, then A second. And these will just give you some product of stabilizers that will stabilize your ground space. But if you do this twisted product, you kind of apply half of, half of the red one first, then half of the blue one, then the other half of the red one, the other half of the blue one. And they end up being kind of interlinked in this funny way, which just basically tells you that you have something like xz on one side and zx on the other. And so to return this into the form of some stabilizer, you need to commute an x past a z. It just picks up a -1. And then when you take the expectation value, you'll have -1 times a stabilizer. So on the code space, with these two invariants, you kind of get something trivial because they're just stabilizers. But this one gives you a -1. And the nice thing is you can blow this up to like a very large region. And then if you define things in this way, this -1 will be like universal on all the deformed toric codes, not just the sort of fixed point one that I'm drawing this nice, neat picture for. So this -1 kind of stays there throughout the phase, and it tells you you have like a non-trivial state. There's no way to get like a -1 here if you started in sort of a trivial product state phase. Is there anything else I want to say about this? Yeah, and one more comment about this. It's quite nice here in this work by Ha that you actually only need one state in your code space. So in the procedure we're doing here, we actually don't really need to have encoded logical information. We only need to have like a topological state. And this was like the sort of genius of Ha. Previous invariants for the lattice of topological order all required a code space. This only requires like some state that sort of has sufficiently big enough patch to do this experiment in, but it doesn't require logical information because you can pull this sort of -1 invariant out of a single state. And that's going to be a feature that our game shares. Good. Okay, does anyone have any questions about that? I think I'm done with topological order. Yeah.
Are there other invariants if you have like more complex knots?
Yeah, there are. Turns out you don't need them for abelian anyons. You can get almost everything out of this S, and then there's also this exchange statistic. There's another procedure for extracting that, which is kind of similar, and it tells you everything. If you have general, like non-abelian anyons, no one knows a full set. No one knows some like finite set of invariants that completely characterize it. But yeah, there's some work in that direction. People have thought of adding a few things and then saying, well, when you add this and this more complicated link, you can distinguish all of these guys and so on. But yeah, this is an open question. I mean, I should say if you have like all knots, you can definitely differentiate two inequivalent things. But to do it with a constant number of them is the question. Yeah, Andrew?
So you sort of maybe implied that it's actually possible to implement. So say I've got some numerical representation of a state, maybe as a tensor network, maybe in terms of something like the hexagonal lattice model, or, that you could actually numerically look for and then these invariants and then evaluate these numbers as a kind of practical measure.
Yeah.
Rather than just saying they exist. Is that correct? Like I could give a student the project.
Yeah, say you want it to be efficient. I mean, what Ha has, I think, is like constructive algorithm, but I think it wouldn't be efficient because you have to do some like funny stuff with an algebra that's very huge. But Jacob Bridgman had this project with Polan and Steve Lemire where they did this using DMRG. They were basically implementing this, but yeah. And say even if you just have like some stabilizer model, you don't know what it is. It's very easy to do there, but it's still a little bit subtle. Like if I want to take some stabilizer model, I don't know what it is, and I want to see how many copies of toric code are in there. This is the best method to do it because there's no chance of getting the answer wrong, basically. Whereas if you use topological entanglement entropy, you can actually get the answer wrong. Yeah. Some questions at the back.
Okay, so I'm not sure if I misunderstood, but that quantity you shown on the right bottom, it looks really local. Like it looks like just a bracket and a vertex.
Yeah.
But shouldn't a topological order invariant be the local quantity?
Yeah, good point. So this is the smallest example, and this will come up later because we don't have a very big quantum device we're using. So we need to play with these small ones. But if you want to like prove rigorous things about local unitary invariance, you basically need this ring size to be very big compared to the light cone of the circuit you're talking about. So essentially, this is like arbitrarily, if you want to talk about thermodynamic limit, these are like arbitrarily large rings, Yeah.
Yeah, with that measurement, if you measure like part of one operator than the other, don't you risk having a non-deterministic measurement outcome there?
Let me think. So, yeah, the actual proposal is that you measure this whole thing basically well, you can break this up into chunks, and then each chunk is just some operator. When you measure them, each individual piece will be non-deterministic, and we'll do that later. But they are kind of constrained, given you started in like the perfect state, they're constrained that their product has to be, the invariant. So like each part could have some like whatever measurement randomness in it, but then they'll like cancel out because you started from a system with some constraint. If that makes sense. So it's sort of okay. Yeah, good. Okay, should I move on? Yeah. All right, now let me tell you a bit about contextuality and how you use that to make up some quantum games. Good. So contextuality, I guess the maybe slightly less famous but also super cool quantum resource compared to entanglement is some nice way to formalize to what extent you can't attach like a hidden variable to the outcome of a bunch of quantum measurements. And so you make these little games. One of them is moment square, where you arrange operators in a grid. And the idea is along each row and column, the operators commute, so you can measure them all at once. And they also have this constraint that their product is either plus or minus 1. So every row and column that isn't this gray shaded one, which is kind of coming up, the product is plus 1. You can go and check, and then on that gray shaded one, it's minus 1. Okay, and the neat little trick of this game is you've set up this kind of Sudoku that's sort of impossible to classically satisfy, but you can quantumly satisfy it. So quantumly, all these constraints will be satisfied, but classically, if you put in binary variables that have to satisfy these constraints, they'll never be able to satisfy all of them. The easy way to see that is that if you add up all the row and column, or multiply all the row and column constraints, there's like a single minus 1. So the product of a bunch of plus 1s with a minus 1 gives you minus 1. But each operator appears exactly twice in a row and column. And so if you look at it on the level of the binary values assigned to each operator, you're taking either 0 or 1, plus or minus, and multiplying it with itself. So it has to be plus 1. So there's no way to multiply a bunch of classical values out and get minus 1 from this table. But you can see with the quantum operators, you can do it because essentially they anti-commute. Okay, so it's like, it's like a neat little way of like just distalizing this. One reason why it's impossible to kind of have hidden variables describe these measurement outcomes. Okay, the previous one I was showing was this sort of state-independent one. It just works on the level of operators. But we're going to work with the state-dependent one, where we actually use some states and make the measurements on that state. And the simplest version of this is given by, instead of this moment square, this moment star. It's similar to the previous game. You have these like rows, but now they go in this sort of pentagram. And the product of these Pauli operators along any line, so here we have also 3 qubits instead of 2. The product along any line, again, they all commute, and they have this constraint that they either give plus 1 on every line except for the shaded one where they give minus 1. And in this case, if you take a GHZ state, which is this kind of 3-party entangled state, 0, 0, 0 plus 1, 1, 1, a cat state if you like, and you look at what measurement outcomes you get in this game, well, the operators along this row all have a definite value when measured on this. They're all stabilizers. The XXX has eigenvalue plus 1 because it just flips these two. The other two have eigenvalue minus 1. Yeah, see if I got that right. The other three. Yeah, good. I think I didn't make a mistake. So these ones all give you minus 1, and it's important there's 3 of them because when you look at the product along this row, you should get minus 1. So plus times minus cubed is minus. Good. And okay, so given that you have this state, these measurement outcomes are already fixed. And then you can look at whether there could be like hidden variables that describe the rest of the measurement outcomes. And essentially, it turns out that it's impossible to satisfy these remaining constraints, that on every other row, you have to be plus 1. And that's because, I have a little plot for this one because it wasn't as obvious to me. Again, every single operator that's outside this row is involved in 2 of these constraints. And then given the fact that you have these plus or minus outcomes along this row, each of these constraints will be either to plus or minus 1. And here I think I'm writing them in like sort of log-based minus 1. So 3 of them end up having to be minus 1 constraints, and 1 has to be plus 1. And then you can see that basically if you add up these top 3, you get the bottom one. But this is telling you that mod 2, 0 has to be 1, which is impossible. So it's kind of a similar game, except here you play it on the GHZ state. And if you use a different state, I think it is possible to satisfy all these. So it's kind of important what state we have. Good. And then you say this is contextual with respect to the GHZ state. I think it's some lingo that essentially you can't have a hidden variable model for all these measurement outcomes with respect to a certain state. Okay, cool. And you can use these neat little algebraic games to create like a multiplayer quantum game. So here I'm going to use this moment star to make a 3-player multiplayer game where there's like a referee and 3 players. I kind of have the dots in here because you can generalize this p equals 3 to any number, but we're going to use the p equals 3, 1 for most of this because it's the simplest one that's sort of non-trivial. And the goal of this game is that the referee will distribute some bits, and then the players they don't get to communicate classically or quantumly, but they can have a prearranged strategy. And they want to return bits to the referee that sum to like half the value of the referee's bit. The sum of the referee's bits he sends out. So let me kind of go through that a bit slower. The referee is going to send out 3 bits here. And there's a promise that basically the sum of them will be even. So it sort of makes sense to take half in mod 2. And then the players, get to do some decision making based on what they saw in the input bit they got, and they decide what bit they want to send back, but they don't get to communicate with each other. They just get to send a bit back to the referee, and they want to satisfy this. So they basically want the sum of their bits to be like half the the bits the referee sent to them. Cool. And you can kind of show, but I'm not going to explain this really, that the optimal classical strategy, it's not really better than kind of guessing. But if you have the GHZ state, there's a quantum strategy so that you allow the players to pre-share this entangled GHZ state. And then given the bit from the referee, this classical 0 or 1 bit, they just decide to measure this GHZ state either in the X or Y basis. And this succeeds at probability 1. I have like a few little slides kind of showing why this happens, but it uses tensor network notation that I didn't want to introduce. So maybe I'll either do it at the end or just ask me offline, and I can show you quickly why that has to be the case. But essentially, yeah, there's always going to be an even number of Y measurements, and there's some constraint between what they can see with what the X measurements can see because you're starting with this GHZ state that makes them satisfy this with certainty. Cool. And then another important point is, what if you don't have the GHZ state, you have some other quantum state, maybe it's very close to the GHZ state, how does this probability change? Well, it ends up moving away from the sort of unit probability with some expectation value of this sort of Merman polynomial of operators, which sort of encodes the game. This is just some linear combination of the operation of the measurements you kind of want to make. And then if you look at the expectation value of this, it tells you, with respect to your state, it kind of tells you if these things start not being stabilizers, it gives you some like kind of error term. And this error term basically reduces your winning probability. Okay. So the idea is that if you have this GHZ state on many parties and you start deforming it a bit, you kind of exponentially reduce your winning probability with the number of parties. Good. And now we just want to make some observations to connect this to topological things. Good. So the simplest one is if you just take this literal Merman star kind of game and look at it from a certain point of view. If you really like Ising models, which are these simple quantum models of stabilizer codes that just have ZZ pair stabilizer checks along a line. This is like the smallest non-trivial Ising model. So it has 3 spins. They interact with the neighbors via ZZ. And this GHZ state is like in the ground space of the Ising model. And in this Ising model, the kind of condensed matter jargon is that we have this sort of symmetry operator or a disorder parameter that will tell us like when we're in the symmetric phase. Then we have these sort of order parameters or order correlators that will tell us when we're in the symmetry breaking phase. And what the operators in this game are doing is basically looking at twisted products of these order and disorder operators. So Z times X is like IY. XZ is minus IY. Maybe I got the signs wrong, but it doesn't really matter because you always have a pair of them. So basically this XYY you can think of as like X, and then the second thing is XZ, the third thing is ZX. So these twisted products exactly just give you these things you measure in the Merman star game. Okay, but the idea is that the Ising model, this simple quantum phase of matter, it's a symmetry breaking phase. It doesn't have topological protection. And so we want to take this idea of connecting the operators you measure here to some twisted products and do it with a topological phase of matter that should have some robustness to perturbations and hopefully do better there. Okay, good. And now I'm going to explain basically just how to embed these like contextuality games into some topological phase. So the square game, you can embed into a topological phase, say the surface code, by essentially just replacing each of these operators you want to measure with some partial string operator. And so the actions mostly going on in this like bottom right-hand corner, the YY, when you embed that into this sort of surface code, ends up being this twisted product. Everything else is just some partial string operators. So you have this like X1 partial string operator and X2 partial string operator, and their product, which gives you a stabilizer of the surface code. Similar for Z. And these strings in space are kind of shifted with respect to each other, although that's not really indicated here. You can see down here. And so, right, when you look at taking these products, basically, you get just these stabilizers and some way of measuring through them, but such that it breaks things up to give you this twisted product when you measure this bottom right-hand corner. And what this does for you is that it basically puts this -1 that's like doing all the work in this square and embeds it into a topological invariant rather than just being some -1 coming from an x times a z. I mean, it is still coming from an x times a z, but if you measure that with respect to a state, it has some universality throughout a phase. Good. And now onto the star one, which is what we actually use. So here the idea is we're going to replace the 3-qubit GHZ state with some sort of 9 or 16-qubit surface code. And the smallest version of this game we can play is over like 4 plaquettes. So this is how things are actually laid out on the surface code. We have these like three squares we're going to use. And then we map the x and z operators in this star over to these sort of partial string operators. So on this x plaquette, you have like the top and bottom of the plaquette and then the 2 sides. On the z, there's 2 plaquettes kind of going on, and so you have like the top cup, the bottom cup, and then this line connecting them. And so with the x measurements, you have to measure you have to multiply all 3 to get a stabilizer. With the z ones, each pair gives a stabilizer. And so this is similar to the GHZ state. So Z1 times Z2 gives you a plaquette, Z2 times Z3 gives you a plaquette, and Z1 times Z3 gives you a pair of plaquettes. And so if you take this middle row and you look at the measurement outcomes of all that on the surface code, you'll get, again, like +1, -1, -1, like we got in the GHZ state. I think I forgot to do an animation for that, but you'll have to remember it. Good, but it's described down here. And so the reason why you get these measurement outcomes, well, the XXX, that's just an X stabilizer, so it should be +1 on the surface code space. But these other ones give you these linking invariants, which are all -1. And the idea here is that this could generalize to like a much bigger surface code patch, although we play the game with a very small one because that's what we had access to. Good, and so this is the basic idea. Want to replace the GHZ state to gain some robustness. And then I can talk a little bit about how we actually did this in the last like 10 or so minutes. Okay, cool. So here's some pictures of the Quantinuum chips, or maybe they're renders, I don't know. And they obviously got like a lot better at making some cool graphic for the second one. We actually ended up having to use both of these because we sort of, some people wanted this to be done in time for the March meeting, and there was one round of data to be collected, and then the H1, which is this one on the left, the H1 traps queue got like super stacked just before March meeting because everyone wanted to get their data for March meeting. And then although somehow the H2 seems more interesting to me because it's got more qubits, its error rates are not as good, so people didn't want to use that one. And so in the plots I'm going to show you, there's a little bit of data from this guy, but that will be replaced for the final version of the paper. Good. And here's a little plot. I took the figure from the H2. I think the 2 devices work pretty similarly, except the H2 is a bit more complicated. But I couldn't find a nice figure like this for the H1, so I'm going to explain the H2 instead. This is an ion trap system, but it's kind of a souped up one. So instead of just having a bunch of ions in some trap, all in the same trap, the way that Quantinuum is making this more like scalable is by making these traps modular. So they have a number of trapping zones, which are kind of shown via these X regions here. And that's where the actual gates are going to happen. So ion traps are cool because you have like very clean qubits. Things are a little bit slow, but you can also have like sort of all-to-all interactions essentially. But they're very like in serial because they sort of all go via the same modes. And what they're doing here is basically having a bunch of little traps that you can move ions into and out of so they can do more gates in parallel. And so I think they can do like 5 2-qubit gates in parallel. That might be with the H1. With H2, maybe they can even do more.
I think it's 4.
4 in parallel? Okay. Oh, on this one. So maybe they can do more with the H1. Yeah, I'll show that one in a second. What are these? I should just explain what's going on in this figure. These are little squares all refer to some kind of electrodes, so some gates, which may be DC or RF. These are to make the electromagnetic potential you need to trap these ions. You have these little rings where you have like sort of an ABC pattern, and that's used to shuttle things around by shifting some voltages. And then I think this first one is just showing how you use like the field to sort of trap some beam, and then load sort of single ions into the trap. Good. Anything else I want to say? And then in these regions, yeah, you kind of do gates on these ytterbium ions. if you kind of have two pulses going on at the same time, you can, so all the logic is going on in this like hyperfine states of these ytterbium ions. And then there are these like Raman processes, okay, that let you manipulate these energy levels, these states. And so if you kind of have this sort of driving by two lasers at once, you can do a 2-qubit gate between a pair of ytterbium ions. And in this plot, there's also this kind of funny little dongles that are going on because they use some beryllium, I think, to help in some way. Don't ask me about that. This single laser is denoting some kind of single qubit gates. And then this slightly different single laser is denoting preparation and measurement, which they do in a different way to the single qubit gates. And then this final thing is just showing some shuttling of these ions around the trap. Cool. And then I wanted to show, so the actual H1, here's like some table you can rip off the internet if you're going to use this device. What are the error rates? So I guess, in the H1, they can do 5 2-qubit gates in parallel. And then the single and 2-qubit gates are really nice fidelities. You get like a 10 to the 4 times 10 to the minus 5 for single qubit gates. They're in 10 to the minus 3 for 2-qubit gates and sort of measurements and preparation. And the gate times, I think, are like microseconds. Is that right? 10s or 50 microseconds? Maybe a bit longer for the 2-qubit gates and the measurements. But if you look at this kind of benchmarking coming from the H2 paper, it's interesting to see that actually those kind of gate times are not really what's determining how long these things take. So each like round of doing one shot of the experiment is like on the order of seconds. And that's because they spend almost all the time moving stuff around and cooling it. So it almost doesn't really matter how slow those individual operations were, because this whole thing is kind of really 1D, and you want to do things that are not 1D. You spend a lot of time just shuffling stuff around and also cooling things back down. Okay, so that's all I wanted to say about the experiment. Probably there are much better people in the room to ask about this than me. But I want to tell you a bit about what we did with this. So luckily, we had someone on the inside who could help us with actually running this, and we probably would have been hopeless. And what we asked them to run is, so first ignore this middle step. We basically want to say just initialize your qubits and ancilla bits, do some round of stabilizer measurements, do some feedback to bring you to the code space, and then, play the game. And then what we wanted to look at was what happens to this game as we do a deformation. So I think this is going into this nice kind of philosophy of, well, what's actually interesting in these early experiments is to probe how things behave when they're not perfect and how well we understand that. And here we add some kind of Y rotation to the qubits initially, which you could sort of think of as controllable coherent noise that becomes sort of incoherent once you measure the stabilizers. And this gives you some sort of disordered, deformed surface code state at the end of the measurement and feedback cycle. And we have like a handle on how deformed it is. And that's what this plot here shows. You start in this sort of topologically ordered phase, the blue region up here, and as you go theta from like 0 to pi, you end up crossing through this phase transition that I think is essentially equivalent to the Nishimori transition for people familiar with error correction. So it's a certain kind of well-understood, more or less disordered phase transition that's equivalent to a like 2D classical stat-mech phase transition. And then you go into a trivial phase where you kind of don't expect any advantage anymore because you essentially have trivial correlations. So we want to see how well the game performs in this phase, especially as we go away from the ideal toric code state up here to a more noisy one. Okay, and here's the plot. So on the left, you have the game. Oh, it's actually a number of games played over the device to kind of average out the positions with some deformation parameter on the GHZ state. So there's also an analogous sort of deformation of the GHZ state we can do, where you deform the qubits with the same kind of unitary rotation before measuring them into the GHZ state. And we thought that was a fair comparison. And we looked at how the GHZ state did for different sizes. So like green is size 4, red is size 9, blue is size 16. And this is still for the 3-player game. So you just play the 3-player game in many different positions on this like 4, 9, or 16 qubits. And you see that in this sort of GHZ state version of the game, you kind of lose, for larger system sizes, you start losing like immediately, basically, even when you have sort of an undeformed state, and that's because there's also like noise. As well as the deformation, there's noise in the device, And what it looks like is happening is you really just sort of lose exponentially in the number of qubits you're using in your game. So this data collapse is basically just collapsing onto an exponential, in some noise rate, an exponential kind of scaling down of the win probability with n, where n is the number of qubits. On the right here, we have the surface code version of the game, where we've only played for 2 sizes because like the size 4 surface code game is not really different. So you really need to go to like size 9 to actually see some effect. And then we couldn't go beyond 16 because of the device we were using. And here you see that like there's this really nice, basically the data points almost fall on top of each other within error bars for the 2 different system sizes. And the point where you lose quantum advantage, so sorry, there's one other feature in this plot, which is you have this like quantum advantage line where your classical strategy will get you up to this line. Above that is like a quantum win, sort of a quantum win probability where you really needed quantum states to play the game. And the place where you cross that is almost the same for these 2 different sized surface code states, whereas for the GHZ states, it's kind of going to the left, and you expect it to go all the way to the left eventually as you make n bigger. Okay, and then maybe I should say what's sort of the expectation if you were to explore this further is that if you could play this game sort of cleanly, where you just have this deformation and not this sort of other sources of noise, that all of these lines would essentially collapse onto each other for n growing, and the point where they cross into the non-quantum advantage should have something to do with the topological phase transition to the trivial phase. Okay. And that takes me to my questions, which is, one is, so how to play this game fault tolerantly. Here we didn't worry too much about other sources of noise that we weren't putting in by hand, but these definitely give you a hit to your win probability. And if you make n really big, they should actually kind of beat you even if you have a topological state. And so for doing this, you need to really worry about like embedding this game into a more of a space-time process that's really robust against noise, all kinds of noise, including the measurements you do of the operators. And then this second point is what I was saying is we think that the point where you lose this quantum advantage should have to do with the phase transition out of the quantum phase. And there have been some other nice research works in this direction where Fiona Burnell and other collaborators have tried to formulate some kind of games point of view, like an actual thing you would do that would line up one-to-one with your topological order parameters, or these topological invariants of the non-trivial quantum phases. And so you'd have some kind of more practical implementation of measuring whether you're in these or not. And I think it's unknown whether we have any kind of games that will be complete invariants and actually match the topological phase transition. Especially ones that are sort of non-adaptive. So our game doesn't change as you rotate theta. And that's what we really want. We want some kind of fixed game where you could say, well, you play this, and then if you get like above this score, you're in the surface code phase. So that's an open question. And then there's finally like sort of a theoretical question that is maybe nice, which is there are some nice cohomological interpretations of contextuality where you formulate these sort of algebraic invariants of these tables of operators in terms of some cohomology. And some version of cohomology also comes into the braiding of abelian anyons, where these topological invariants come from. And probably it's the same, but I guess that's also an open question. And so that's where I'm going to leave you. Thanks for your attention.
I want to ask the first question, but it's a vague one. So I think it's pretty clear if you actually had encoded logical qubits, that you could find a robust version of the game that uses those logical qubits. But that's not what you're doing here. You're using a system that has a logical qubit, but that's sort of not used. You're appealing to these topological invariants, which you can imagine even being in a system with no logical qubits. So. Yeah, my vague question is, do you have anything to add to that resource, that it's sort of a robust property that is
lesser than logical qubits, but still non-classical and useful for something.
Yeah, you said actually what I should have said when I formulated it, which is that sort of trivial you could just make fault-tolerant qubits and then play the game on them, right? But we don't want to do that. We want to just have, say, a single state and some procedure that's sort of fault-tolerant, which would be a little bit outside of it. It would probably end up being in some way similar to playing the game with actual surface code qubits. But I think that we don't fully understand that, like making some braid you would do in space-time sort of fault-tolerant against how you would actually measure it out. I don't think I have much to add there. I think it's an interesting question.
So I understand in the GHZ case, I understand how the games play, you distribute elements of the GHZ state to the players. I didn't follow how that works for the surface code. Presumably each player only gets a fraction of the pre-agreed state, is that right?
Yeah, sorry, I didn't say that. But yeah, in the surface code game, we play it on different patches, but basically you chunk it up and you say like, you get this bit, you get this bit, you get this bit, and also maybe the referee will keep some. Say it's a really big surface code, you can just play it with like your little bit, and your little bit, and then maybe the referee prepared the full. Sorry, I said it completely wrong. The players prepare the surface code and distribute it beforehand, but they don't need to distribute all of it. There could be like some other party holding some part of it. They just need enough, basically. But yeah, essentially you just choose some subsystems.
I didn't follow that.
Yeah. It depends on how you map these invariants into the thing. But I think in this small example, for guy 1, they need like basically this top part. The bottom one needs this part, and then the middle person needs this part. So the top person will get these 3, the bottom person will get these 3, and the middle person will get these 2. And then they could also get this one or not. You don't actually use that one. Yes.
So there's this program of compiling non-local games so as to do hardware verification with crypto primitives in the middle. Have you thought about whether there's something interesting to do here? Like, does this enable an easier implementation of some of those verification protocols in any way?
Yeah, interesting question. I actually have no idea about that, but it sounds super interesting. And I guess maybe you want to play them in somehow a fault-tolerant way. Maybe there'd be some reason to think about these things, to embed them into a protected invariant, but I'm not sure.
The basic idea is you're compiling a multiplayer game to a one-player game with which is carried out sequentially in time, and you're replacing the non-locality with a cryptographic primitive.
Mm-hmm.
And it's been proposed as a way of doing verifiable testing of hardware. So.
Yeah, it sounds cool. Maybe I'll check it out.
Andrew.
So you were just talking about how you hand out bits of the system to the different players. Is it part of the rules of the game that the qubits that I get as a player have to be logged in the underlying code?
No.
No.
I guess it would actually work in this one, but there'd be some contiguous patch. But I mean, yeah, maybe I think generally in this game, if you weren't to modify it, it would just be like you're allowed to share some quantum state on some qubits, but there'd be no rule that has to be local. But I guess we could define a new version where it is local, but we didn't think about that too hard. Yeah.
So if you scale up the surface code, you mentioned that your operators need to be big enough to capture the topological features, but have you looked at how the advantage scales with if you fix the size of some big surface code and then change the size of those operators? Does that affect how much of the...
Yeah, we do have you can kind of convert this quantum wind probability into a StatMech model, which you can, it's not quite exactly solvable, but you can evaluate it. So we do have some numerics on how those things change, but you do lose a bit when you make the operators really big and then you deform away from the perfect state. And so this is one of the things maybe you'd want to deal with by making either an adaptive version or a fault-tolerant version of the game. Or there are other ideas you'd have to kind of rescale, because your operator ends up being some big kind of not perfect thing, and the bigger the non-perfect thing is, the kind of further away you are from the answer you want. And so what people have done in numerics in the past to measure these kind of operators in a numerical simulation is to try to rescale them by some, there's some like expectation value of just like a loop with no linking, and that kind of tells you the scale you're looking at, but it would impact your performance a bit. Yeah, I don't know if that fully answers your question.
Yeah, so like when that explicit example you got there on the screen, what would happen if you just kept those operators, but then you scaled up the surface code outside of its boundaries? Like you just make the surface code bigger, but keep those operators the same. How would that change the?
Yeah, as long as the scaling up is not making the qubits kind of more noisy, you will have the same win probability. Like if you kind of, what we did already is we averaged over a couple of positions you could put this in, and we had like 2 versions, one where there was like a bigger surface code, and you can see it doesn't really change the win probability, the average win probability, which is this slide. Like these are sort of averaged over the different positions you can play in on these 2 sizes, and they end up being basically the same.
All right, let's thank Dom again for a great question.